Please welcome to the stage Singularity University's Faculty Director and Vice Chair of Medicine and Digital Biology, Dr. Tiffany Vora.
Good morning, friends. It's such a pleasure to be here, not just with you today in this room, but also in Edmonton. It's actually my first trip to Edmonton, and I've been taking a poll. If there's one thing I should do, what should I do? And the answers are 50-50 split between Riverwalk and go to the mall. So I have a tough decision to make tomorrow. I think it's mostly going to depend on the weather. So if we're here today, I am here to talk with you about the future of health. Some of you we've met down in either the youth stage or down on the forum stage where we've gotten into some of these topics. And I've also been hearing some really nice discussions from my colleagues here on the main stage about how some of these technologies are impacting food and other types of areas of daily life. So for right now, we're going to focus on your experience as a patient, as someone who needs healthcare, what it means for your families, and how things are changing now and what they're going to look like in the future. So here's kind of what healthcare looks like right now, right? You wait until you have a sign or a symptom, and that sends you to your healthcare provider. If you're lucky, you get to see them pretty soon. If you're not so lucky, you have to wait. And then that human doctor makes a decision based on the information that you've given her and maybe some other information that she has. And then she tells you to do something different. Eat less, exercise more, take this pill, take these 2 pills, take these 10 pills. And then you wait to see if the sign or the symptom goes away. Dr. Daniel Kraft, our chair of medicine, has really characterized this as sick care. In contrast, we are predicting that the exponential technologies that you've spent the last day learning so much about are going to radically transform sick care into health care. That means you're not just waiting until you get sick to go to the doctor, but you are being supported by a continuous real-time stream of many different data types, which are quantitative and in many ways qualitative as well. And all of that information then can be fed into algorithms, AI, machine learning, all of which can give you a course of preemptive action to take before you ever get to the point where you're actually sick. Then we have a whole other suite of technologies that would be reinforcing behavior change, right? So if you are trying to exercise more, being on some kind of social network where you get to get up there and brag on every time you finished one of your runs or have your friends give you thumbs up on Facebook, those are really great reinforcing behaviors. And that is an important sense of this healthcare, real healthcare, that what we're looking for. In the future then, we're going to move away from this very high cost, very doctor-centric, and very time-intensive paradigm that we are currently using for sick care, and instead transition to lower-cost, patient-centric, and continuous healthcare. Now, what's interesting to me about this is all of those affordances also come with them some really interesting questions about how we handle these data, how do we regulate these systems, and what is my duty as a patient, as an empowered patient, in terms of managing my own health. So the first piece of this is information abundance. So I want to take a step back for just a minute and talk to you about what we call digital biology here at SU. And I've heard some of my colleagues giving you the beginnings of this, but let's go ahead and just do it together. So as a refresher, all life on Earth is related. All life on Earth is made of cells, including you. And if you take one of those cells and you zoom in on the cell all the way down to the level of the chromosomes, you get to the operating system of life. Now, how many chromosome pairs do humans have? You should all know there's a famous DNA company named after it. 23. You have 23 pairs of chromosomes. And you can think of those chromosomes as the operating manual for you. If you zoom in further on those chromosomes, you get down to the level of the famous double helix of DNA. And what that is, of course, is a chemical structure. It's something you can actually touch. And it's made up of 4 chemical bases that, for short, we call A, C, T, and G. Interestingly, just last month, that number of base pairs doubled, which was exciting for me. It's still not natural systems, but it means that this is really changing fast. So here's where the digital part comes in. As soon as we were able to read A, C, T, and G on a chemical molecule and transform it into computer A, C's, T's, and G's, then those 6 Ds that you've learned about meant that the life sciences could now ride that wave of digitized information in order to become truly exponential. The last piece I want to point out here is that DNA evolved on Earth to be an information storage mechanism. So computers store information as zeros and ones. Life on Earth stores information as A's, C's, T's, and G's. So anything we can do to computer code, we can also do to DNA code, right? So if we want to move big pieces of DNA around, that's called genetic engineering. We've known how to do that since the 1970s. If you want to write DNA from scratch, that's synthetic biology. We're getting way better at that. And if you want to go in and debug the code of life 1 letter at a time, you do that using gene editing technologies, including CRISPR, which is the most famous one that I know you've heard a bit about. So all of those technologies are piggybacking on this idea of life as information. So this wouldn't be a talk at Singularity if I didn't show you an exponential curve. So please note the log scale on the y-axis, which means that an exponential curve will come out to look like a straight line. So you might remember back in 2001, the draft sequence of the human genome was published simultaneously by the Human Genome Project and also Celera Genomics. And at the time in 2001, the price of that whole project was about $2.7 billion, and it took 10 years to complete. So I'm showing you here the price performance of DNA sequencing. And what you can see is that the price performance of DNA sequencing approximately followed Moore's law until 2008, when something important happened. A new type of sequencing technology was invented that had different types of the actual chemistry of the reaction was different, but the computational back end was different too. That technology was given the name next generation sequencing. We're actually on to the next version. Do you want to guess what it's called? Next generation, yeah. So innovators, think carefully when you name things because it matters. So what you can see from this point is after 2008, the price performance of DNA sequencing began radically outperforming Moore's law, all the way down to in 2015 when we hit $1,000 to sequence a human genome. Now to put that in context, in the United States, that is more affordable than getting an X-ray. Okay, so that says a lot about my country's healthcare system. But what it also tells me, though, is that we are coming to a point where getting DNA sequencing is going to be so cheap, it's actually going to be expected. In fact, several companies are predicting that the marginal cost of DNA sequencing will be pennies on the dollar within the next two to 3 years, quite frankly, which means that within 5 years, DNA sequencing will effectively become free. So what that means then is that we are going to have a wealth of information about the DNA of living things, not just human DNA, but your DNA, and your DNA, and your DNA. Raise your hand if you've already gotten your genome sequenced or done something like a 23andMe kit. Quite a few people. Okay, so I think that's only going to become more prevalent. And here's where it also gets interesting if we go back to those 6 Ds. Back in 2001, this is what the DNA sequencers looked like. They were about the size of a refrigerator. They cost about $1 million a piece. We still have big, expensive machines like this in order to do DNA sequencing, but let me show you another way that a DNA sequencer looks today. This is a handheld DNA sequencer by a company called Oxford Nanopore over in the UK. I had one and I was going to bring it to show you guys, but the TSA gets a little twitchy when I take things like this through airport security, so I went ahead and left it at home. But it is a handheld DNA sequencer that plugs into a laptop by USB, which is astonishing. They've come up with a new version of this sequencer called the Smidge Ion, which plugs into your smartphone. So imagine a world that's not very far off, where everyone can be walking around with DNA sequencers in their pocket. That raises a lot of really important questions about DNA privacy and things like that. Some people feel very strongly that they want to keep their DNA private. I take a slightly different view for that as a biologist. Every one of you right now are leaving behind the DNA on everything that you're touching, right? You're unpeeling something to eat, you're holding your badge, you've got your phone, you're holding a notebook. You're leaving your DNA behind on every cup, every chair, everything you touch. So if I really wanted your DNA, I could wait for break when you guys all go get coffee. I could come get your DNA, and using my handheld DNA sequencer, I could sequence your DNA without your permission. I'm not going to because I'm a very busy woman, so you're safe from me. But what that tells me is this idea of me trying to hold on to my DNA information doesn't actually make a whole lot of sense to me, because I'm giving the physical molecule away all the time, and the potential to decode that information is becoming democratized. So there's a lot of interesting questions here that I fully admit I don't have all the great answers to, but they're important questions because of the speed and the pervasiveness of these technologies that are critical drivers of healthcare. And DNA information is only one type of information we can get from your body. So there's a whole suite of things, from blood tests. By the way, have you guys seen the Theranos documentary? You should watch it. Yeah. So it's worth watching, friends. So whether it's blood tests, whether it's VR, AR, whether it's chemical signatures, metabolomics, RNA, proteomics, all of these different types of things we can measure now and quantify using a variety of devices. How many of you are wearing a wearable right now? Yeah, here's mine. It's shiny. I like it. It's pretty. But all of those things are generating enormous amounts of data, all of which are being used now, today, to train algorithms that are becoming ever smarter and ever better at delivering real-time, personalized, actionable insights to you. That's the future of healthcare. So you can see that we're moving away from this reactive paradigm in which, for example, you wait until you get a headache to go to your doctor does an MRI and finds you have a brain tumor. Instead, we're moving toward a proactive future in which I think every person will be sequenced, their whole genome will be sequenced at birth, if not before. If you do this via IVF, if you have a baby through IVF, you can take one of those cells out at the 16-cell stage, sequence it, and the embryo develops just fine, which blows my mind. It's kind of amazing. But picture a future in which every child is born with a risk portfolio that maps to their DNA and other types of models that we have. If you knew that you could half your child's risk of colon cancer as an adult by raising them vegetarian now, would you do it? If you knew that getting them on a sports team so that they got an hour of exercise every day would cut in half their risk of having a heart attack in 30 years, would you do it? These types of questions are really important ones and are all predicated on this idea of abundant information that gives us personalized insights. We're not there yet, by the way. If you Google risk portfolios, you'll see that the data are getting much better and better as we get more and more data feeding into these statistical algorithms. But with an abundance of data comes a really important question. Who owns your health data? Friends who did 23andMe, who owns your health data? Do you know? Did you read the end user license agreement? Yeah, so the answer, for very reasonable reasons, is that 23andMe owns that data. So they can take your data, they could sell it on to anyone they want, they don't have to ask you, and they don't have to tell you. Lots of businesses operate on that business model. But I would like to suggest that there are other models that we should be looking at. And this type of disruption is in the healthcare system called bio-brokers. So bio-brokers are folks who are figuring out how to take this abundant information we have about our own health and putting the patient, you, at the center of all of those marketplaces and transactions. So let me show you just one example of this, because there are several companies in this space. So Nebula Genomics is a company that has come out of George Church's lab at Harvard. If there's one place, by the way, that you want to watch for all the crazy stuff that's going on in biology, watch the Church lab. I am his scientific granddaughter, so I am biased, but I'm telling you, whether it's woolly mammoths, new DNA marketplaces, new types of sequencing, they're doing it. Okay, so the way the Nebula Genomics platform works is you, the individual, are placed at the center of that marketplace. You answer some questions, health-related questions, a questionnaire, and then you decide to have your DNA sequenced. And you can either pay for that yourself, or there are marketplace ways where you can earn Nebula coins, credits, in order to offset the cost of your sequencing. That information is stored in a really cool advanced cryptography way that's decentralized. So if a hacker gets into the database, they don't get everybody's DNA. So that's great. And then the information gets pushed back to you. Now here's where the marketplace part comes in. Now you are able to anonymize your data or partially anonymize your data to contribute to a pool of anonymous data that Nebula is able to use for research purposes. That earns you those tokens, those credits. And then from there, pharmaceutical companies and researchers who are interested in the disease that runs in your family or in the DNA that you have can offer to pay you for access to that information. All of those requests are stored on a digital ledger, a blockchain-based ledger, that is permanent, transparent, and unchangeable. So you have a permanent record of every company or lab that is asked to see your DNA data, and a permanent record of whether they have permission to actually use it, and you can charge them for it. So again, you earn more credits in a blockchain-based currency to keep this cycle moving. So this is really interesting to me because their pricing model is interesting. While I was sitting in the green room waiting to come up to talk to you guys, I just went onto their website to double check, and Nebula is actually running a sale where the kit, instead of being $99, is $9.99, and then it's a $7 a month subscription fee afterward to participate in the marketplace. So $7 a month is like your Spotify account, right? So, and yes, you can do this in Canada. I double-checked that for you as well. So again, this is just one company that's operating in this space, but I think you can see how disruptive this business model is to the way we've done health research in the past and what health research and healthcare will look like in the future. So then we have all these data. Who protects you and who protects your health data? This is really interesting in Canada because in 2017, y'all passed the Genetic Non-Discrimination Act. It was adopted by your federal parliament. And the point of this law was to make it so that people wouldn't feel that a medical insurer or an employer could get a hold of that DNA and discriminate against you. We have a similar law in the United States. It's called the Genetic Information Non-Disclosure Act, Non-Discrimination Act. It actually took the lawmakers in the United States longer to write our law than it took to sequence the human genome. So, May 2017, that was when this passed. But then, of course, the insurance companies pushed back and said, how can we possibly accurately model risk if we don't have access to the data? And so for a variety of reasons, governments of Alberta and Quebec objected to this law, said that regulating insurance and this type of thing was a matter for the provinces, not for the federal government. So it came up in front of your courts, and in 2018, the Court of Appeal ruled in favor of Quebec and said the federal government doesn't actually have the power to make it safe for people to use their genetic information. So the main purpose of this act was to promote the health of Canadians, and what it's turned into is a federal-province political struggle over who gets to regulate. So this case is scheduled to go in front of the Supreme Court of Canada in fall 2019, and I suggest keeping your eyes open on this because this is really important. If your boss can discriminate against you based on your DNA sequence, are you going to choose to have information that could hurt your employment but could potentially help your life moving forward? These are really important questions. So I've mentioned that healthcare solutions are going to be increasingly personalized and digitized as we move forward. That goes for diagnosis, for therapy, and for discovery. So let's take a quick look at all of these things from the patient's point of view. So diagnostics is a really obvious place where convergent technologies, particularly your smartphone, are going to be really empowering for this. So, you know, Dr. Sunny Kohli, who is joining us here as SU Canada faculty, is one of the winners of the Medical Tricorder Prize from the X Prize, right? So these things are happening right now, whether it's your smartphone helping you with particular conditions, whether it's a wearable helping you with your exercise. How many of you have an Apple Watch? Are you using the EKG function to see if you're an AFib? That's really, really interesting that you can use just a regular watch for that. And then, of course, there are all these other functionalities that are being digitized so that instead of the doctor's office being crowded with a series of devices, you can have them dematerialized into smaller and single devices, or even have them in your pocket as you're walking around in your daily life with you. What's interesting to me about this is this changes what it means to be a doctor. And my colleague Philip is going to be talking to you about that next, so stay tuned for that. And just as an example of one of these that I think is a really important and powerful example of convergent technology, let's just talk about skin cancer for a second. So a couple of years ago, a group at Stanford took images, almost 130,000 images of skin lesions, mostly moles and skin cancers, and they had both the images and a physician's diagnosis as to whether that lesion was actually cancer. And then what they did was they took that giant data set and they trained a deep neural network on it to be able to learn what's, cancer, no cancer. Any Silicon Valley friends out there? Hot dog, no hot dog? Yeah, cancer, no cancer. And then what they did after training the network was they went and got a bunch of new images that the network had never seen before, and then looked to see how good the network was at diagnosing the new skin lesions. And it turned out that this algorithm, this machine learning, was as good or better than 21 board-certified dermatologists at diagnosing more than 2,000 diseases. So this is spectacular for a whole bunch of reasons. Number one, in Canada, it can take you 6 to 9 months to get an appointment with a human dermatologist. But I am telling you about a neural network that could be turned into an app on your smartphone. So as a patient, that's really astonishing, because you don't have to wait 9 months to see someone who can tell you whether you have a cancer and whether it's growing. It's also important for dermatologists because diagnosing skin cancer is only a really small subset of what dermatologists do. So I would argue to you that we're actually empowering our doctors by handing off tasks like this to machines, which empowers the doctor then to focus on other things. And again, my colleague Philip is going to be telling you more about that in the next session. So this is very exciting, and I would watch for more and more types of applications like this. We've also seen some beautiful examples here in the last couple of days of how personalization of healthcare extends to non-organic materials, right? So whether it's personalized 3D printed prosthetics, whether it's skin grafts, which we'll talk about more in a minute, other types of implantables and wearables, all of these therapeutic options are becoming available to us with greater and greater frequency. Even the building of exoskeletons to help the elderly so that they don't fall, or to help soldiers carry heavy loads, or to help warehouse workers lift things repetitively, right? To get an assisted lift from these 3D exoskeletons. It's really a beautiful version of how convergent technologies are driving therapy in healthcare. Let's look at another way that you could actually program your health using living things, where the biology is the technology. So induced pluripotent stem cells are what I would argue is one of the great scientific advances of the last few years. That's why the Nobel Prize for this was given out not too long ago. And an induced pluripotent stem cell, which I'm going to call an iPSC just so I finish on time. iPSCs are great because what you can do is you can take something easy to access from your body, like a skin cell, and then dial it back to being a stem cell. And then from that stem cell, that iPSC, you can then dial it forward into other types of cells that you can use for other purposes. So let's say, for example, you needed a kidney transplant. If I were to take some of your skin cells, dial them back to a stem cell, and then theoretically dial them forward into a kidney, and then I put that kidney back in your body, would your body reject it? No, because it's your kidney, right? It is absolutely personalized to you. So what you should be asking is, hey, Tiffany, how do we 3D print kidneys? And so it turned out on April 15th, a group in Tel Aviv claimed to have 3D printed a heart from human stem cells. Now, the heart came out to be smaller than a rabbit, and I haven't actually seen the data. I went looking for the primary report, but I wasn't able to find it, so I'm still watching that. But what would be another way that we could grow organs? So we could grow them, can't grow them in people. I don't know if you guys read that Ishiguro book, but I did. What about pigs? So if we could take your cells and grow them in a pig so that an organ, your organ, grew in that pig, then we would have a way of harvesting that organ from a living pig and putting it back into your body, and it would be a personalized, potentially perfect genetic match for your body. I'm not joking about this. There is actually a company right now, actually it's another one of George Church's companies now that I think about it, growing these piglets in order to grow human organs in them. Now my question for you is, if a pig has a human heart, is it human? If a pig has a human brain, is it human? So future of work statement, we're still gonna need lawyers. So encourage your kids to go that way, but it's a really interesting question. Another thing I can do with your stem cells is make you in a dish. So there are these things called organoids where I can take the stem cells and then I can encourage them to differentiate into cells that would form an organ in a petri dish. And they're not perfect. You can't just like grow a heart, that doesn't work, or grow a brain. But I can get an organoid that has the same layers as the brain and potentially responds to drugs and things like that in a similar way. So if you have a cancer, I could take your cancer cell, grow it as an organoid in a dish, and then expose it to all of the chemicals, the drugs that I'm thinking of using for your treatment, and we can check ahead of time whether your cancer is actually going to respond. I think that's a really powerful way for personalized drug discovery. One of these companies in this space is called Emulate Bio. I'm showing you their organ on a chip. That's the size there. And what's really cool is you get beautiful things inside it that actually grow to look like organs. So this is a lung organoid and this is an intestinal organoid as they look inside these organs on a chip. So stay tuned for more of this. Now here's where things get interesting. I've told you that life is information, and I've told you that all life on Earth runs on the same source code, and I've told you that now that source code is open source. So by the way, my colleague Julie is going to be up here next just showing you how you can be a bioengineer as well to program in this source code of life. So if we are able to do all these things, then now is the time we need to be asking really important questions like, is it okay to edit an entire species? I could edit every mosquito on Earth right now to never give another human being malaria. That's a very powerful thing, and it's the first time in history we're poised to that. But if I can do that to mosquitoes, I can do it to humans too. And if you've been watching the news, you probably see where I'm going with this. So what's interesting is that gene editing, so going in and debugging the source code of life, can be used for therapy in two ways. One way is where you just change your body. That's called somatic editing. And somatic editing has already been tested in various places around the world. Now what's interesting is there was a balkanization of ethics on this, where originally we were seeing China racing ahead in this field because they were not part of a voluntary moratorium on this kind of research that folks in the West had asked for until we could resolve some really important ethical problems. So China was moving ahead, and they are still way out ahead, especially in cancer therapy with gene editing. What about Canada? Well, as it turns out, Canada actually has a law that will put a scientist in jail for innovating in a way that would have the edit passed on to another human. So last year when I was in Canada and I was talking to some government folks, they said, how can we make Canada a leader in this space? I was like, don't put your scientists in jail. That would be step one. So you can see this article came out in late 2017, okay? So a year and a half ago, where people are saying if we're gonna drive innovation in Canada, we have to decriminalize this. And then you might remember that last fall, things got really interesting. So MIT Tech Review in late November broke the story that two baby girls had been born in China who had been gene edited. AP picked it up, and then the scientific literature went crazy. By the way, this scientific result was announced on YouTube, okay? Not in the scientific literature. Whole lot of problems about this that we can talk about if you'd like to come find me. But the morals and the ethics of this are really important. This is just from a couple of days ago, where one of the Stanford professors who knew about this had been under very severe investigation for not having told anyone. And what he kept saying was, who am I supposed to tell? There's no science police. There's no science jail. So how are we moving forward as a species on this? The WHO has convened a panel so that we can actually have, hopefully not science jail or science police, but science consensus where many stakeholders are coming together to discuss the future of how we design ourselves as a species, because that's what we're doing right now. And this is the framework that I use to think about these questions, and I'd like to present it to you. I ask 4 questions. The first question is there a need for this technology? That's like a public health question. Question 2 is, can it be done? That's a technical question. I'm a research scientist. I really like technical questions. Is it legal? That's a regulatory question. And question 4 is, should it be done? That is a moral question and an ethical question that is much harder to answer, but we don't get to pass the buck on this to our kids. These technologies are here now, and we have to make decisions now about who we want to be as a species and who we want to be as people. So here's what we've talked about today. All life runs on the same open source operating system that outputs data. The biology is the technology. Medicine is going to be increasingly personalized in real time. I bet you can see that even today. It's only going to increase as we move forward. And these technical, ethical, and moral questions need answers now, because as we're reaching for this abundant future, we are faced in a really unique point in history, and now is the time for every one of you to be empowered as a change maker. Remember, the future doesn't happen to you. You design it, and that's true for your own health as well. Thank you all very much. I'll see you soon.